In this video, we'll deal with the concepts of infiltration and flow in the vadose zone. How do we characterize these processes, and how do we measure them in the field? So a principle that we'll use to characterize these processes is the mass balance or conservation of mass. And to apply that, we'll draw a control volume here. And the flow into the control volume equals the flow out plus the change in storage. And so if we imagine this scenario where the rainfall rate is 3/4 of an inch per hour, so that's a flux across this control volume, and the rate flowing out is 3/4 of an inch per hour. These two are equal, and so there's no accumulation of water and there's no flow downslope, and so simply the rain falls on the ground and it soaks in. Okay, so that's interesting, but we can we can make it a little more interesting by boosting the rainfall rate. So let's say we double it, and by doing that, we increase the infiltration rate to 1 inch per hour, but it's not increased enough to keep pace with the rainfall. And so then if we draw the control volume, what happens is that we've got 1.5 inches going in, 1 inch infiltrating, and we have 1/2 inch per hour flowing out of the control volume as lateral flow or runoff. Okay, so we have this simple balance approach for determining whether we could have runoff or we just simply have all the rain infiltrating. This will have important implications because this runoff can lead to flooding or increases in the stage of a stream. We might also imagine that if this surface was fairly flat, instead of running off, then we might have water accumulating and forming puddles or shallow ponds. This is a process that is called ponding. So the balance between rainfall, infiltration rate, and runoff will be an important concept. So we can extend this concept by bringing in this idea of infiltration capacity. And this is the maximum rate with which water can infiltrate into a soil. Now, during a rain, we might imagine that this capacity would decrease as the soil becomes wetter. The infiltration capacity, the rate at which the water could infiltrate into the soil, is going to decrease with time. So we draw this curve and we intentionally leave off any units because we're just trying to get the concept of infiltration capacity and that it decreases with time during a rainfall. And so if we apply to this a unit hyetograph, and a hyetograph is a plot of the rainfall as a function of time, and it's typically displayed as a histogram type of plot. And so here we have what we'll call a unit hyetograph. So this is the rainfall rate as a function of time, and the rainfall rate is just constant. So a very idealized rainfall. Then what we see is during this early part of the rainfall, the rainfall rate is less than the infiltration capacity. And in that case, the first situation that we saw on the previous slide is what would occur. All of the water that's falling as rain infiltrates into the ground. But once we reach this point, the infiltration capacity has decreased and it's now less than the rainfall rate. And so we have the rainfall rate exceeding the infiltration capacity by this much. And so in this case, we're creating runoff because we're having more rain fall on the surface than can infiltrate in. And so this is now the amount of infiltration that would occur because it's first of all limited by rainfall, then limited by infiltration capacity. And that little wedge of rain here that we cut out is what flows over land, or it's going to be overland flow or surface runoff. Okay, so that's a way to come up with a simple quantitative estimate from what might happen. And we can look at this conceptually in cross section. If we apply rain to this, say we have a vertical cross section, and we'll have infiltration proceeding downward. This is now a region where it's wetted by the rainfall and infiltration that's occurring, and this wet region migrates downward. This front here, which is the leading edge of the region where the moisture content is increased as a result of infiltration, this we'll call the wetting front. So the wetting front moves down, and we've got some water stored up here as a result of this process. And so with continued rain, the wetting front moves down, and the moisture content up above it increases, but it may reach a saturation point. And when it does that, when the surface soils become saturated, then we can have ponding occurring. And so here we've got the water building up as a result of the rainfall rate exceeding the infiltration rate. And so that results in the water accumulating at the surface. And so if there's a slope, we could have overland flow. If it's flat, then we would just have ponding. So then what happens? The rain stops and the sun comes out, and we start to have some evaporation take place. And so the process of evapotranspiration occurs, and now the flow of water is upwards. So at the ground surface, we're removing water, and down here at the wetting front, it continues to move down. And so the question would be, will this water end up as recharge? Because we have these two competing effects. The ET is causing water to move upwards and go out of the hydrologic system, go out of the subsurface hydrologic system at any rate, and gravity is causing water to move downwards. The rate at which it moves downwards will slow with time, however, if we don't replenish it. And the question is, will it keep going and make it down all the way to the water table and then be recharged? Or will it just simply get hung in the vadose zone and then get removed by evapotranspiration eventually? When we characterize the storage of water in the vadose zone, we have several terms that result, and these terms are ratios of the different components. And to see how this works, let's take a look at this little sketch. And if this is a representative volume of porous material, then we see at the various highest level we have some solid materials and some pores, the material between the solids. And the pores are occupied in part by water, and in this case there's some space, some pore space that's filled with air. So we can make just a very idealized diagram and say, well, if this is our representative volume, then part of that volume consists of pores or voids, and part of it is solid. And we can further characterize that as a pore space that is filled with water or air. So we might just cut that in half and say, well, there's water in there and there's air in there. Okay, so just a very idealized conceptualization, and we could represent or we could measure these different components by either determining their volume or their weight. Okay, so with that in mind, let's take a look at these different terms. The first one here, the water content. This is also called the mass wetness in some circles, and it is the ratio of the weight of water in a sample to the weight of solids. So we're using this weight characterization, and we're taking the weight of the water here to the weight of the solids in a representative sample. Now, what we'll use to express the amount of water in a soil is the volumetric water content. This is probably the more common usage, and it's a ratio of the volume of water in the sample to the total volume. There are then several unit weights that are used. The total or the bulk or wet unit weight is the total weight of the sample taken as a ratio with the total volume. So we weigh the sample, we measure the volume, and we take the ratio, and that's the bulk unit weight. The unit weight of water is pretty straightforward. The dry unit weight of the sample would be the weight of the solids to the total volume of the soil. And then the last unit weight here is the unit weight of the soil solids. So that would be the weight of the solids to the volume of the solids. So in that case, we're ignoring the volume of the pore space, and we're just really focusing on the volume of the solid material. And then we've got some terms here that involve the porosity and related. So porosity, we've seen before, it's the volume of voids taken as a ratio to the total volume. A related term is the void ratio, and it's the ratio of the volume of voids to the volume of solids. So related to the porosity, but instead of taking the ratio with the total volume, it's taken with respect to the volume of the solids. And then the degree of saturation will be an important term in the vadose zone. It's the ratio of the volume of water to the volume of pores. So the saturation of 1 is a completely saturated material, and then as the material becomes unsaturated, we get a degree of saturation that's less than 1. So we can determine the basic properties of soil by doing a simple test where we take a sample and we measure the volume of the sample and we weigh it. That would be step 1 here. And then we put the sample in an oven, and the traditional way to do this is to dry it at 105 degrees C. And then we put it in and dry it for several hours or overnight, and then we weigh it again, and that's step 3. And we weigh it again, and the difference between the weight after drying and the weight before drying, we assume is a result of the loss of water that's been removed during the drying process. So by taking the difference in the weights from stage 3 and stage 1, we can determine the mass of water, and we just assume the density of water is known, and we can then determine the volume of the water. And so from those data, we can determine these 3 things pretty easily. W, this is the weight of the water taken as a ratio to the weight of solids. And so we know that from this drying test. The bulk unit weight is the total weight taken as ratio to the total volume, and the dry unit weight is the ratio of the weight of the solids to the total volume. So we can determine these ratios fairly easily, and then these other terms we can come up with, we can calculate using these formulas. And so if we start with these terms, then these formulas give us a way to calculate these other things. So the volumetric water content is related to these 3 terms using this formula. We could also determine the volumetric water content as the volume of the water over the total volume, which we would have from these measurements. And here's the calculation for porosity in terms of these unit weights. One thing that I should point out is that typically what's done is to use just an estimate for the unit weight of the solids, and this is done by just assuming that the mineralogy is either quartz or clays, and using this as an approximate estimate for the unit weight of the solids. If you do that, then you can calculate what the porosity is. because that term there, that gamma sub s, it needs to be known for the porosity calculation. So the void ratio is related to the porosity, and you can then also calculate the degree of saturation using this expression. Now, one thing that I should point out is that in order to do the calculations that I've shown here, you have to be able to determine the volume of the sample as it's obtained in the field. And this needs to be the volume that the soil occupies in place. So it's what's called the undisturbed volume. And if you can make that measurement, then you can go through and do these calculations. But if you can't, if the soil has been disturbed during the sampling process, then you can't determine the unit weight and the bulk unit weight or the dry unit weight, because you can't determine this total volume. You also won't be able to determine the volumetric water content because it requires knowing the total volume. So if you can't obtain an undisturbed sample, then you're going to be limited in these terms that you can determine. However, if the sample is disturbed, you can still go through the process of weighing it, drying it, weighing it again. That'll give you the weight of the water that is in the sample, and then the final measurement is the weight of solids. So you'll be able to get this term W, the water content, simply by weighing it, even if the sample is disturbed. So under ideal conditions, you're going to determine the volume of the sample that you obtain and under undisturbed conditions. And that allows you to determine all of these different parameters. But if you can't, then you can still determine the water content by weight.